So good morning, dear colleagues. We are Martin Pecka and Sergio Cacamo from the Trader project. And we've come here to share our experience from the last 4 years of the search and rescue project heavily utilizing ROS. We'll start with a short introduction of the project so you'll know what it is about. Then we'll have a look at the ROS tools and packages we've created to solve some problems we faced. You'll also hear something about the more advanced functionalities that can be treated like having some scientific importance. And then there will be a funny section of our experience with hardware. And the last is a secret section. Stay tuned for it. I think it's worth it. So Trader is an EU-funded project which aims at enabling humans and robots to form search and rescue teams. And we really concentrate on the end users. So we need to create robots and interfaces that are helpful to the firefighters in finishing their missions. The tasks for the robots include exploration of disaster areas, detection of something in them, monitoring the areas, and depending on the mission, it can also include like sample pickups, measurements, whatever the firefighters ask us to do. We really try to concentrate on mutual cooperation between humans and robots, so it's not the usual way when robots are providing useful data to humans. But we also try the other way around, so that humans get that robots get important information from the humans. And the robots need to work in an unfriendly environment. We have no markers in the area. We have no pre-trained models. We cannot depend on geometrical assumptions because the buildings we are moving in are usually collapsed. And so on. There is smoke, fog, smoke, sorry. And yeah, it's really the most unfriendly environment for our robots we can imagine. So the team comprises of a team leader, which is so far always human. Depending on the mission, there can be in-field rescuers. And because it's a robotics project, there are always ground and aerial robots which do some tasks assigned by the humans. The robots have some operators. So far, it's a one-to-one mapping, so one operator to one robot. But our aim is to alleviate this so that like one operator can handle more robots by providing more autonomy to the robots. All of these actors are represented as software agents in a multi-agent software framework, which allows us to do high-level reasoning about what's going on right now in the mission and provide some useful information. So, for example, there is a speech recognition layer which listens what are the firefighters talking about. And if it recognizes a task assignment, it can, for example, put some high-level information like the team leader assigned a task to the UAV operator to get an image of some area. And the system expects that the UAV will move to that area, take a picture, and that the picture will need to be shared to some other colleagues of these firefighters. And all of this is stored in our set of high-level and low-level databases. We'll cover that topic later. The ground robotic team members are custom-made tracked vehicles. We have 5 of them. They weigh about 25 kilos, so they're not too big, but also not too small. And definitely they cannot rescue people. They can detect everything, but they cannot drag the people out of the mission area. The robots usually connect via Wi-Fi. They have multiple cameras, a tilting lidar, and depending on the mission, we can attach a lot more sensors, including tactile sensors, smoke sensors, gas, radioactivity, whatever the firefighters ask us to put on the robot. And the ground robots intentionally do not have a GPS because they are expected to move in buildings. In the UAV area, we still haven't found like the holy grail, so we are experimenting with the commercially available ones. We started with Ascending Technologies drones. Now we switched to DJI Mavic Pro, and we're still not sure if we are at the point where we would be satisfied. Nevertheless, the goal or the requirement for the UAVs is to provide live RGB streams so that the firefighters can get a quick overview of the disaster area. And if possible, we also require them to provide infrared streams. And these drones can use GPS because they're flying outside. Each operator has 2 screens in front of him. One is the usual operator control unit. Ours is based on RQT, so we have, you see there, ROS, some camera plugins, and some hardware-related control plugins. And the UI is modular, so that every operator has only the UI elements for the particular sensors attached to the robot at the time. The other display shows the tactical display system, which is common for all the firefighters in the mission. And it's the interface between the humans and the high-level reasoning system. In the right part, you can see some notifications or warnings generated by the high-level system or from the other team members. The middle part shows the overview map, which might be taken from Google Maps or from the UAV overview images. And in this map, in the lower right corner, you see icons that represent robots, human team members, and some localized disaster dangers like fire, biohazard, whatever we find and want to share with other team members. Peeking into the mission command track, we can see the team leader down there. You can see he's facing the tactical display system, and on the lower display, he has a screen where he can request live camera streams from the robots in mission. Next to him sits the UAV operator, which is now like manually operating the UAV. And what's important, you see he only controls the UAV using the screen. He has like no direct view on the UAV. The same holds for the ground vehicle operators in the back. They also teleoperate the robots without having direct sight on them. That was the intro, and now let's jump right into the particular ROS packages we've created. So the first problem we faced was the number of packages. We didn't start from scratch. We are continuing a previous project from which we inherited like 100 of ROS packages, and we needed to add more and more. So we needed to somehow structure that. Since we were using Git, we tried using submodules for a while, but we quickly decided not to do that because we found it too confusing for the developers to use them correctly. So now we use about 15 Git repositories that are separate, and we can only install the repositories that are really needed on all the machines, like the operator machine doesn't need the robot drivers installed, and so on. What we found quite useful is having one repository with all the message and resource definitions that's present on all of the machines in the system, so that you can quickly visualize and publish messages from every machine that's connected. But we're still not satisfied with the point where we are, but since it's the last year of the project, we won't be able to change that. But if you are starting your new project, you might do better than us. So if you can create auto-installation scripts, that would be really helpful for the new members joining your development team. We are not able to use ROS install because we have some external dependencies that are incompatible with that. But again, like if you can use it, it's quite useful. Our developers have free choice of build tools, so they can freely use like Catkin Make, Catkin Tools, Catkin Simple, whatever, which is good for the developers, but not good for the integration of the project. And last, we use our own GitLab installation, which is nice that we have the data, we own them, but it's quite demanding to maintain it. Another problem we faced early in the project was network congestion. As you heard, we have many robots acting at the same time in the same area, and we request video and point cloud streams from the robots, and that's a lot of data. So we at least wanted to solve the issue that, for example, if 3 operators subscribe the same video stream, so that the stream is not transmitted 3 times over wireless, but just once. That is why we chose to use a multi-master solution based on the Nimbro network framework. We adjusted a bit so that it supports latched topics and bidirectional communication over topics. And it solved part of our problems. So here's the layout. Each of the robots runs its own ROS master. And then we have one ROS master for all the local machines connected via wire to a switch. So that if the 3 operators subscribe the UAV stream, the stream is just transmitted once from the UAV to the server we have on the local side. And then the stream is multiplicated on the local gigabit network, which is no problem. So This solved some of the problems, but some still remain, like Nimbro network doesn't support disconnecting of the topics which nobody is interested in, so the data are transmitted like just all the time. And if the network goes out, it sometimes doesn't go back quite nicely. The configuration for the Nimbro network is also quite cumbersome, so we created like an auto generator for these configurations based on simple YAML configurations. So you just specify like the robot will transmit this topic to the server, and the generator will generate the proper config files. It's not yet released, but we plan to do it. As the whole system is highly modular, we needed a tool that allows us launching just parts of the system. We have a lot of drivers, but not all of them need to be running at one time. So we had the choice of either writing a big bunch of launch files for every possible situation, or opening up 20 terminals and typing the launch commands in them. Neither of it was like good for us. So we created this tool we call Trade Orchestra. It's again configured by some simple YAML files. And it generates this set of windows. You can see each column corresponds to one machine in the network, and there are buttons which more or less corresponds to launch files. So you click the buttons first time, it starts the launch file. If you click the second time, it kills it. And you can see the red one. That means the launch file has died for some reason. And what showed to be quite useful to us is launching all of these files in separate screen sessions. So if something gets wrong, you SSH to the machine, open the screen session, and you have just output of that one single failing part. And the output is not interleaved with the output of the other nodes. We're sure it's like not the only way to solve this problem. Yesterday I've seen here like some more meta launching tools. Each of them was nice. So we decided not to publicize this because we think it's too specific to our project. But if you think it would be valuable to us, to you, come to us, talk to us, and we can share it. Having many attachable sensors is not only a problem in launching their drivers, but also it's a problem for keeping an up-to-date 3D model. So what we created, or why do we need an accurate 3D model? That's, for example, for laser filtering, camera image masking, and also for the operators. They're usually quite interested in the precise outer shape of the robot. So we created this tool which takes as input a XACRO file, which is parameterized. And depending on values of these parameters, for example, if the robot has or has not the robotic arm, it generates a URDF file that contains or does not contain the arm model. We found also quite useful to be able to change the model during runtime, because we sometimes know that we forgot to attach some sensor, so we quickly attached it, and we don't want to restart the whole system to make it aware of that sensor. So we connected with dynamic reconfigure, and you can change these like has arm or does not have arm parameters during runtime. And the usual static robot description parameter is not sufficient for that, so we created a dynamic version of that parameter, and all the nodes that need to react to changes in the 3D model are subscribing to the dynamic changes in this parameter, and they can update their internal representation with the new 3D model. This is not yet released. We are still not sure if it would be valuable for someone else. Another issue we faced was when we tried to simulate the tracked robot we have. We opened up Gazebo, we opened up other simulators, and found out that there is no way to simulate a tracked robot in a way that would be suitable for us, so that the robot can overcome like difficult obstacles and so on. So we created, we think, a better model than all the available ones, and compared this model to all the other models we have found in existing simulators or in the literature. And it's a teaser for my Wednesday presentation at ROS. So if you're interested in this tracked robot simulation, come there and listen to me later. Or you can ask me anytime else. And this, for example, enables us to do reinforcement learning with the tracked platform. As a zoom camera can be also attached to the robot, we faced another problem, and that's the lacking support for zoom cameras in Camera Info Manager. So we took the Python version of it and added 2 approaches for zoom camera calibration. The first, more proper approach is to calibrate the camera at several zoom levels and then interpolate the camera matrices between the closest 2 calibrated levels. Or if your camera has discrete steps for zoom, you can calibrate all of them. And the less proper or more coarse way is to just open up the manual of your camera and lens, read out the values like field of view and sensor size, and put them in the script, which generates a very coarse calibration. It might be sufficient for some uses, but definitely not for rectifying the images, for example. We found the integration of this into ROS packages is difficult because they usually don't expect camera info to change. And the C++ part is also not done, so if you want to use it in C++, the ideas are there, but just in Python. Each robot can carry more than one pan tilt and maybe also zoom-capable camera. And we needed an interface where the single operator can view and control all the streams from these pan tilt cameras. So we created this RQT widget. On the left side, or right side for you, you see there's a dynamically updated list of cameras available right now at the system. The operator can select the camera stream of interest. By clicking in the camera image, he issues relative positioning commands for the pan tilt unit. And in the lower part, you see a 360 panoramic image, which serves an absolute positioning tool. And by clicking in that absolute panoramic image, the operator issues the absolute positioning commands for the units. The number of independent actors in the system brought us to completely new challenges in mission data storage. Of course, if you have one robot, you store data in bag files, that's okay. But either if you have more robots and actors in the system, like the human operators, the speech recognition system, and so on, or if you want to access historical data during runtime of the same mission, it's not sufficient, or it wasn't sufficient for us, so we created this system of low-level and high-level database. So basically, the low-level database is a MongoDB with support for large file storage, for example, camera streams. All ROS nodes can put data in this database using some dedicated ROS services, and the data are stored there for later use. Then we have the middle layer, which we call semantic modelers. They are ROS nodes, which do not connect to the ROS topics, but instead read data from the low-level DB and transform them into some semantic information. As an example, we have a low-level fire detector, which tells you at position X, Y, Z and time t, there was a fire detected. And we have 200 of these detections, but we don't want to report 200 fires to the firefighters. We want to cluster these detections to one big fire, and that's exactly the task of the semantic modeler, and so that one big fire is then reported. And the last layer is the high-level database, which is Sparkle DB with some ontology we've created or crafted for the search and rescue scenarios. And this high-level database then allows semantic question querying, and we use the goal framework to implement software agents deliberating about what's going on. For example, if the system or if the team leader gives commands to the UAV to fly somewhere, and the system knows that the battery level of the UAV is too low, it can warn the team leader that the task will not be possible to be fulfilled by this UAV, and the team leader can then decide to assign the task to someone else, for example. Last in this section, I'd like to tell you about something I'm not sure I can recommend you to use, but I still think it might be good to know it's there. It's our easy-to-use way to use TensorFlow in C++ and ROS. So the problem was we had some pre-trained graphs in TensorFlow, and we wanted to do inference on them on the robots. But to do it in C++, you have to install the build system of TensorFlow, install a lot of dependencies, and the build takes years, maybe. So we didn't want to go all this way on the robots. So instead, we misuse the Python installed TensorFlow library. We created a set of CMake scripts that locate this installed library on your computer. So you just type pip install TensorFlow, And the CMake finds this installed library and then allows you to link against this library. So it's quite easy to just write C++ TensorFlow inference code, and then these 15 lines of code enable you to build it in ROS. It's definitely not good for training because the library Python installs is not optimized, so it's not even including like SSE2 instructions, which are, I don't know, 10 years old. So the inference isn't fast, but if you have like some simpler graphs, it might help you. And now the floor is Sergio's, and he'll tell you something about the more advanced functionalities.
Hi, everyone. So I'm going to give you just a quick overview of some of the many functionalities we develop in Trader that were designed to address some of the many problems we encountered during real deployment of robots, and that somehow motivated our research efforts. Scientific contribution in Trader spans on many different areas, from manipulation to vision to multi-robot collaboration to control. So I will start with mapping. So as we said, Trader is a teams-oriented project. So we have teams of UGV, UAVs, and humans sharing information, collaborating. So in this work, we merge information coming from different UGVs into the same map. So we have in this image 3 trajectories of robots. You can see the red one, the green one, and the yellow one. These are 3 UGVs that are exploring different areas of the map. And then we build this common representation, which is the white one, on real time on CPU. So this is publicly available. You can check the code over there. I'm not going to go more in details because this will be presented during ROS. So feel free to come and ask questions there. So information comes not only from UGVs, but also from UAVs. So in this other work that will be presented as SRR in Shanghai soon, we not only merge ground information coming from the UGV, so LiDAR point clouds, but we also merge aerial reconstructions, basically aerial views of the scene together. So I'm not going to go into details on this one too. Feel free to ask questions later. So the problem with this kind of, when having multiple UGVs and when we have a search and rescue operation is how to optimize the time that we have so to explore a wide area. So if we deal with a situation when we actually have to act in a very, very short time, we don't want to send 2 robots exploring the same region of the map, but we want to optimize this. So we implemented this 3D multi-robot path planning for patrolling. It works in 3D, so even with maps with multiple floors and with complex environments. So it's based on a 2-level decision-making architecture. So the first one is a topological level where robots cooperate to distribute over the graph in order to minimize the average node idleness. And the second one is just a metric level. It basically takes into account the geometry of the map, so roughness of the terrain, obstacle, and so on, in order to constantly replan traversable path to the goal position, taking into account also location of other robots and other team members. So this will be available soon if you want. It's all in ROS if you want to check it out as well. So on a different problem, so communication, wireless communication is problematic. We know that. We have seen this one in other talks. So search and rescue robots really require stable communication with the base station, no matter if the robot is teleported or not, because we always want a constant video feed. We want to know what's happening on the robot location during a search and rescue operation. If there are victims, we want to send a rescue team ASAP. So unfortunately, stochastic element in radio signal propagation, like shadowing or multipath fading, leads to signal loss. And then what happened to a rescue robots is that it's either abandoned if it loses signal, or it tries to backtrace the way to the base station, which is not always possible because the access point is moved around many times or the map changes. So we try to do this resilient communication aware motion planner that basically is a system that allows to dynamically online map the radio signal strength distribution over the geometric map and adapts to changes in the radio signal distribution. And it also proposes a self-repair strategy in case the robot loses connection. So it brings the robot back to a connection-safe location. So this is an example of how the system works. With we have this UGV that is exploring this very small area. So the green points are the traversable points. The robot is mapping the environment. Red one are obstacles. At the same time, the robot is building the Wi-Fi distribution on the environment. So you see this bell overlapping the map. Red regions are not connected area. Yellow one are poorly connected areas, and blue ones are very well connected areas. That yellow blinking thing over there is the access point. So if at some point we select a point in the map and the robot has to autonomously go there, it doesn't choose the shortest path to the destination, but it goes towards a location that is very well connected. So we try to avoid signal loss. At the same time, we can reestablish connection if the robot mistakenly goes on a non-connected area. Finally, another big problem in search and rescue robotics is the control of multi-degree of freedom mobile manipulator. This is a very tricky task, not only in search and rescue robotics, but especially there because we have very strict time constraints, not so skilled users, limited field of view, delays, constant delays. So our solution was to vision-aided the Cartesian arm control. So we basically try to detect samples on the environment, and then we guide the arm towards the samples, and then we let the user just do a small adjustment and finally pick the samples. So these were just a few of the many functionalities. We don't have time to go over all of them. Feel free to ask questions later and check our website, and I'll let Martin conclude with the hardware section.
Thanks, Sergio. And now it's time for the funny, or maybe not that funny, hardware experience section. Depends on you. So USB cameras. Raise a hand who of you have used USB cameras on your robot and they worked like a charm. Perfect. So it's not just that we would be unlucky in our selection, but maybe it's just a general property of USB cameras in Linux. I don't know. Nevertheless, we wanted to somehow summarize our experience during the 4 years and many sensors we have tried. So if you would be selecting a new USB camera, there's this to-do list, like check it's supported by the Linux kernel. You don't have to build it into the kernel, but it's really there. And that it doesn't, for example, crash your kernel after some time of use. Then check it's supported by ROS, which a lot of cameras are, but still it's a good check. And last, do not connect the camera to your laptop when testing it. Connect it directly to the robot, running on battery, running a stress test, and then assess the performance of the camera. We had one camera that was really nice, connected to laptop, but connected on the battery-powered robot, it gave us one picture in 5 seconds. Wow. And when we would be so lucky to design a new robot, we would make sure it has enough USB-free ports directly on the motherboard without any extender cables, that we are able to screw the cables to the motherboard. And if the motherboard has some USB 2 ports, we would make sure they get more than half the amp power that's in the standard, because, for example, Asus Action Pro sometimes draws more than the half amp. And if it's not there, it just dies. Maybe that's just a dream, but we would like to have a USB bus for every port, because some devices don't like each other on the same bus. Whatever. If you want to read like the particular experience with all the sensors we have tried, you can read it later. We'll not go through it right now. The link to the presentation is in the upper corner, so you can review that later. Okay. Our experience with wireless communications is better, though. We started with 2.4 gigahertz Wi-Fi. It didn't work. The bandwidth is just not quite good enough for us, and you know, the spectrum is usually too crowded. So we switched to 5 gigahertz Wi-Fi with some like powerful antennas and so on, but still in the legal area. And we were quite nicely surprised. Even like 200 meters away from the base station, we got the reception about like 20 megabits per second. When the robots are closer, we get up to 100 megabits per second with multiple robots in the field together. So that's really nice. It even worked in a furnace, which was like walls made of 5 centimeters of steel, and it still worked there. Nice. But then we got in touch, just in short touch, with a military-grade radio-based mesh network. That was awesome. 32 megabits per second for half a kilometer. Wow. But it's illegal. You know. And recently, we've also created a custom emergency radio link, which is quite slow, 200 bits per second. But it works up to half a kilometer, and we can send some emergency commands to the robot over it, or we can request an emergency video stream, which means one picture in 1 minute, for example, to just know what happens to the robot when it lost its Wi-Fi connection. Again, you can later read the particular hardware we use or we have been using. Last in this section, I describe our experience with the LiDARs and depth sensors, because they can also be another source of problems. We're using them for several purposes. We want to do metric mapping. We want to use some reactive control algorithms taking into account the 3D environment of the robot. And last but not least, the scans are also useful to the operators when they need to teleoperate the robot through some narrow passage. They really like to use ROS and look around the robot, how to traverse the path. But each of these uses requires a different quality or type of the point clouds, so we use multiple sensors on the robots. First, what's always there is the rotating SIG LMS laser scanner, which is a 2D laser scanner. We had to add this rotation mechanism, which keeps breaking. But when it works, it provides us nice 3D scans up to 50 meters, outdoor, perfect. But just the mechanical tilting is a problem. We would like to get rid of it, but we still haven't found a suitable alternative, not moving. And we are quite looking forward for the solid-state LiDARs. We even had some ideas about how to do better mapping with them, even though they're not there yet. We've also tried ASUS Pro, which you probably know works very well with ROS, but it's probably superseded by the Intel RealSense series. We got in touch with the R200, which is structured light plus stereo on board, which is nice. It works indoor, outdoor, up to maybe 20 meters. But we just noticed that the variance in depth measurements is quite high for us. Maybe it's just we can't configure it correctly, but the variance in 5 meters was, for example, 1 meter for us at some occasions. And now we can reveal the secret section. So even though we had all these problems you heard about, and the environments are quite unfriendly, and we have to shift the system towards the end user needs instead of the programmer's needs, we were able to actually use it in reality. So we had a real deployment of the system in Amatrice in Italy last year. There was a strong earthquake which killed almost 300 people and totally destroyed the city. And there are 2 churches that were quite damaged by the earthquake, but still standing. And the firefighters asked us to do some structural assessment of these churches, both from outside and inside, so that they can then decide about what to do next with these churches, if they can be repaired or if they should tear them down. So we took both the ground and aerial robots, and first the aerial robots did this overview of the area, then they flew inside the church actually, which was quite complicated. We used the views from 3 aerial robots to get the 1 aerial robot inside, to just be sure that it doesn't crash. And then when we knew how does it look from the inside, from the overview aerial, we sent the ground robots inside, doing the detailed 3D maps using the rotating laser scanner, and they were teleoperated. There was no autonomy in this mission because we really did not want to lose the robots inside the church. But still, the data the robots created were quite useful for the firefighters. And here you can see a structure from motion reconstruction of one of the churches. And this is the inside reconstruction. Okay, so that was all from our side. Here's a bunch of links for you. We have released some of the software I've talked about, or Sergio talked about. Be sure to check out our YouTube channel. There's a lot of videos, either from the training mission or from the real deployment in Amatrice. And we've also released some search and rescue data sets, which might be also interesting for you. So thanks for your attention, and now it's time for questions.
A reminder for those of you who want to come questions, we've got the 2 microphones. Please come and speak to them so that the recordings and live stream can hear you.
Hi. What kind of operator control unit were you using? I saw there was like a screen, but it didn't look like a laptop. Were you using just a laptop to control the robot remotely?
No, we're using either the Logitech gamepads or Microsoft gamepads.
Okay. And my second question is, so when you were using the laser inside, there was a lot of trouble. Did you have issues with scratches on the laser or something like that, laser getting damaged, and did you take protective measure for that?
Well, the operators took utmost care of not damaging the laser scanner, and I think it's also like very well positioned on the body of the robot, so that if the robot crashes into a wall, the laser scanner is protected by the tracks.
Okay, thanks.
But of course, like if you bump into a rock, it can get damaged, and but it's quite like industrial, so it lasts.
Thanks.
What software have you used for the reconstruction of the point clouds? We have seen the churches here, and it looked really nice. So.
Yeah, so it's called SegMatch. It's available. It's on the slides, so there will be released.
Yeah, that's also correct. So,
and it was developed by ETH. It's just a SB base.
Okay.
Okay, any more questions? If not, let's thank Martin, Sergio again.